The year is 1943, and the most wanted man in occupied Europe is suffocating in the bomb bay of a British Mosquito aircraft. Niels Bohr, 58 years old, lies curled in darkness as the plane climbs toward England. The oxygen mask doesn't fit properly over his large head. His consciousness begins to slip away. Below him, Denmark, his Denmark, falls into the distance. Behind him, 5 colleagues remain trapped in Copenhagen, their fates unknown. In his mind, the equation that explains how uranium splits. In his hands, nothing. He carries no papers. Everything he knows about the atom exists only in his memory, and that memory is fading as oxygen deprivation pulls him toward unconsciousness. The pilot, unaware his passenger is dying, pushes the aircraft higher, following standard protocol for crossing occupied airspace. The Mosquito's twin Merlin engines drone steadily, their vibration transmitted through the metal fuselage into Bohr's body. He can feel the cold seeping through his coat. The bomb bay was never designed for human cargo, and at this altitude the temperature has dropped below freezing. His fingers are numb. His vision has narrowed to a tunnel, then to a pinpoint, then to nothing. The last conscious thought he has is of Margrethe, his wife, left behind in Sweden, not knowing whether he will survive this flight. Then even that thought dissolves into the gathering darkness. In 30 minutes, Bohr will either arrive in England as the man who can unlock the atomic age, or arrive as a corpse. The outcome depends on whether his brain can survive the next 1800 seconds without adequate oxygen. This moment, this man struggling for breath while carrying the keys to unimaginable power, represents the end point of a 30-year journey that began with a simple question about why atoms don't collapse. The journey from that question to this suffocating darkness contains within it the entire transformation of physics, from certainty to uncertainty, from clockwork to probability, from academic pursuit to geopolitical weapon. To understand how we arrived at this moment of crisis requires going back to the beginning, to a time when atoms were still theoretical, quantum mechanics didn't exist, and a young Danish physicist was about to discover that the foundation of reality itself was stranger than anyone had imagined. Before we dive into how Niels Bohr revolutionized our understanding of matter and found himself fleeing for his life with the secrets of the atomic bomb, take a moment to like this video and subscribe to the channel. Your support means everything to me, and I'm genuinely curious, where in the world are you joining me from today? Drop a comment and let me know. Copenhagen in 1885 was a city of gaslights and horse-drawn carriages, a small capital that nonetheless considered itself a beacon of Northern European culture. The Danish Golden Age had passed Golden Age, but its afterglow still illuminated the cafes and university halls where intellectuals debated philosophy and science with equal fervor. The city's narrow streets still followed medieval patterns, winding between buildings that mixed Renaissance grandeur with bourgeois restraint. The harbour smelled of fish and tar, of commerce and the sea that had made Denmark's fortune. In winter, fog rolled in from the Baltic, turning the city into a landscape of shadows and lamplight. In summer, the long Nordic days stretched until nearly midnight, and the parks filled with families taking the air. Into this environment, on October 7th, Niels Henrik David Bohr was born to a family that embodied the union of intellect and privilege. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, a man whose research on how oxygen binds to hemoglobin would earn him 2 nominations for the Nobel Prize he would never receive. Christian was a large man with a commanding presence and a methodical mind. He approached biological questions with the precision of a physicist, measuring and quantifying where others had merely observed. His laboratory was filled with custom-built apparatus for testing respiration, for analyzing blood gases, for understanding the mechanics of life at a chemical level. His mother, Ellen Adler, came from the Adler banking dynasty, one of the wealthiest Jewish families in Denmark. The Adlers had risen from modest origins through banking and finance to become establishment figures in Copenhagen society. Ellen's father, David Baruch Adler, had been a prominent banker and philanthropist who had financed numerous cultural institutions in the city. Ellen herself was well educated by the standards of her time, fluent in multiple languages, versed in literature and music. She had married Christian in 1881, bringing both wealth and intellectual refinement to the union. Though she had converted to Christianity upon marriage, as was expected in such mixed marriages, her Jewish heritage remained part of the family identity, never discussed but never entirely erased. The household was one where dinner conversations routinely involved the leading scientists and philosophers of Scandinavia. The Bohr home at Bredgade 62 became a kind of salon where ideas were currency and intellectual performance was valued above all. Young Niels absorbed an atmosphere where ideas mattered supremely, where intellectual rigor was the highest virtue, and where the pursuit of truth was considered both noble and natural. He learned to listen before speaking, to consider questions from multiple angles, to value precision in thought and expression. These habits, formed in childhood around the family dinner table, would define his approach to physics for the rest of his life. Christian Bohr ran his home like a seminar, encouraging debate and intellectual combat among his guests. Visitors included the philosopher Harald Høffding, whose ideas about the limits of language and knowledge would later profoundly influence Niels's thinking about quantum mechanics. Høffding argued that language was inherently limited in its ability to describe reality, that words captured aspects of phenomena but never their totality, that different descriptions could be equally valid while apparently contradictory. These ideas, absorbed by a young boy listening at the edges of adult conversations, would resurface decades later when Niels confronted the paradoxes of quantum mechanics and developed his principle of complementarity. The boy listened as his father and colleagues dissected problems from multiple angles, debated interpretations, demanded clarity of thought. One evening in 1897, when Niels was 12, the conversation turned to the nature of scientific progress. Was it linear, each generation building on the previous? Or did it proceed through revolutions, old theories collapsing under the weight of new evidence? The physicist Christian Birkeland, visiting from Norway, argued passionately for continuity, for the accumulation of knowledge like bricks in a wall. Høffding countered that history showed discontinuity, that Newton had overthrown Aristotle, that Darwin had overturned the fixity of species, that progress often meant destruction of cherished ideas. Young Niels absorbed this debate, filed it away, not knowing that his own career would vindicate Høffding's view that he himself would become one of the revolutionary destroyers of classical certainty. This methodology, approaching a problem from every conceivable perspective until its essence emerged, would become Niels's signature intellectual approach. But the household also provided something else, the understanding that science was not separate from life, that the questions one asked about nature connected to questions about how to live, how to think, how to understand one's place in the universe. For Niels, physics would never be merely technical. It would always carry philosophical weight. He would never be able to separate the question, how does nature work? And from the question, what does it mean that nature works this way? This integration of technical and philosophical, empirical and conceptual would make him both a great physicist and a frustrating one. Great because he asked deeper questions than most, frustrating because he could never quite articulate answers with the clarity his own standards demanded. He had two siblings who shaped his development in different ways. His older sister Jenny would become a teacher, quietly competent, but overshadowed by her brilliant brothers, accepting this subordinate role with what appeared to be grace, but may have been resignation. In the Bohr household, intellectual achievement was the measure of worth, and Jenny's more modest talents consigned her to the margins of family attention. She would remain close to Niels throughout his life, managing practical matters, caring for their aging parents, providing the kind of domestic stability that freed her brothers to pursue their more celebrated careers. The family dynamic replicated a pattern common in that era: women supporting male achievement, their own contributions invisible or undervalued. His younger brother Harald, however, was Niels's match in brilliance and perhaps exceeded him in natural talent. Harald displayed a mathematical facility that seemed almost supernatural. He could see patterns in numbers that others couldn't perceive, could manipulate abstract symbols with a fluency that left his teachers astonished. He became a mathematician of considerable reputation, making significant contributions to number theory and complex analysis. And he played on Denmark's Olympic soccer team in the 1908 London Olympics, an achievement that filled Niels with both pride and a hint of competitive envy. Niels had played soccer too as goalkeeper, but never reached Harald's level. The brothers were inseparable as children, testing each other's ideas, engaging in intellectual combat that sharpened both their minds. They would spend hours in the family's summer house at Tisvilde, a small beach town north of Copenhagen, walking along the shore and debating problems. Harald would propose some mathematical puzzle. Niels would approach it methodically, sometimes taking days to work through it while Harald solved it in hours. But Niels's solutions, when they came, often revealed deeper structures that Harald's quicker intuition had missed. It was a productive complementarity. Harald's speed and Niels's depth, Harald's facility and Niels's persistence, each pushing the other toward excellence. Yet even in childhood, differences emerged. Harald was quicker, more facile with abstract concepts. Niels worked more slowly, grinding through problems with almost painful thoroughness. Where Harald dazzled, Niels persisted. Harald could attend a lecture, grasp the essential points immediately, and move on. Niels would need to work through the material multiple times, approaching it from different angles, questioning assumptions, rebuilding the argument in his own mind until he possessed it completely. This difference would define his approach to physics. Not brilliant flashes, but sustained, relentless contemplation until understanding emerged from fog. It also meant that Niels's achievements, when they came, were built on deeper foundations than Harald's. Harald was brilliant within existing frameworks. Niels would eventually shatter the frameworks themselves. At school, Niels proved capable, but not spectacular. He attended the Gammelholm Latin School, a traditional institution that emphasized classical languages and rigorous academic discipline. The school occupied a stern stone building near the harbour, its classrooms cold in winter, its atmosphere one of strict formality. Students wore uniforms, addressed teachers with elaborate honorifics, learned through memorization and recitation. Niels chafed at this approach. He was known for asking questions that teachers found difficult to answer, not because they were beyond the curriculum, but because they probed the foundations of what was being taught. Why this assumption? What justifies that step? When the mathematics teacher presented a geometric proof, Niels would ask whether the proof depended on the particular diagram or worked for all possible configurations. When the physics teacher explained that heat was the motion of molecules, Niels wanted to know how we could be certain that molecules existed, whether the theory could be anything more than a convenient fiction. His grades were good, but not exceptional. What distinguished him was the quality of his doubt, his unwillingness to accept explanations that didn't satisfy him at a deep level. This could be frustrating for instructors who sometimes saw his questioning as obstinacy or showing off. His Latin teacher wrote on one report card, "Satisfactory progress, though the student would benefit from greater acceptance of established authorities." Niels was bemused by this comment. For him, established authorities were precisely what needed questioning, not out of rebelliousness, but because understanding required examining foundations, not just accepting conclusions. It also meant that when Niels finally accepted something, he had understood it with unusual completeness. He didn't just know that Newton's laws worked. He had worked through the logic that led to them, examined the evidence that supported them, considered the alternatives that Newton had rejected, internalized the entire conceptual structure. This thorough, almost obsessive approach to understanding would serve him well in physics, where apparent contradictions often dissolved upon deeper examination, where quick answers were often wrong answers, where patience and persistence could unlock insights that brilliance alone missed. He entered the University of Copenhagen in 1903, intending to study physics. His father hoped he might pursue physiology instead, following the family tradition. Christian even arranged for Niels to spend time in his laboratory, exposing him to physiological research, hoping to kindle interest. Niels found the work interesting enough. He helped with experiments on blood oxygen levels, learned to use the equipment, developed appreciation for careful experimental technique. But physics offered questions that seemed to touch the very nature of reality, and that was where he needed to go. In physiology, you studied how living systems worked. In physics, you studied the foundations of what existence itself meant. The questions were more fundamental, more austere, more absolute. His early university work showed the same pattern: slow, thorough, occasionally brilliant. The University of Copenhagen in the early 20th century was a small institution by European standards, but it maintained high academic standards and had produced several notable scientists. The physics program was led by Professor Christiansen, an experimental physicist known for precision measurements of optical phenomena. Christiansen ran a traditional program. Students learned classical mechanics, electromagnetism, thermodynamics and optics through lectures, problem sets and laboratory work. It was solid, conventional physics education that prepared students to become teachers or work in industry. It was not designed to produce revolutionaries, but Niels found mentors who encouraged deeper thinking. Professor Christiansen recognized something unusual in this methodical student who worked through problems with such painstaking care. He began assigning Niels special projects, giving him access to the laboratory outside regular hours, engaging him in conversations about the philosophical foundations of physics. What was light, really? Was it wave or particle? The wave theory had triumphed in the 19th century, explaining interference and diffraction beautifully. But certain phenomena, like the photoelectric effect recently observed, seem to require particle-like behavior. How could light be both? Christiansen didn't have answers, but he encouraged Niels to think about such paradoxes, to not be satisfied with theories that worked without understanding why they worked. In 1907, at age 22, Niels won a gold medal from the Royal Danish Academy of Sciences for experimental work on surface tension of water. The achievement marked him as promising, but it was experimental physics, measuring, apparatus building, precision work. He had designed an elegant experiment using vibrating jets of water, measuring surface tension with unprecedented accuracy, confirming theoretical predictions while also revealing small discrepancies that suggested the theory wasn't quite complete. The work required patience, skill, and meticulous attention to detail. It demonstrated that Niels could do careful experimental work when required. It also paradoxically revealed what he was not. He was competent with apparatus, but he lacked the instinctive feel for instruments that characterized great experimentalists. His hands were large and somewhat clumsy. He broke glassware, struggled with delicate adjustments, found the physical aspects of experiment frustrating rather than enjoyable. What would emerge later was that Niels's real gift lay elsewhere, in theoretical insight, in the ability to see patterns and contradictions that others missed. But he didn't yet know this about himself. He continued with experimental work, completed his master's degree in 1909 with a thesis on electron theory, and began a doctoral thesis on the electron theory of metals. The thesis work occupied him from 1909 to 1911, 2 years of grinding through calculations, reading everything available on how electrons behaved in metals, developing a theory that could explain electrical and thermal conductivity. The work was competent, thorough, and relatively conventional. It extended existing theories rather than challenging them. It earned him his doctorate in May 1911, making him Dr. Bohr at 26. It did not mark him as a revolutionary. That transformation was about to begin. The catalyst was England. In 1911, Bohr received a grant from the Carlsberg Foundation, the same foundation that would later fund his institute, to spend a year abroad, studying at the leading centres of physics in Britain. For a young Danish physicist, this represented the pinnacle of opportunity. Denmark was peripheral to European physics. The real work was being done in Germany, Britain, and France. The Carlsberg grant would allow Bohr to work with the leading physicists of the age, to learn cutting-edge techniques, to make connections that could define his career. He chose to spend the first part of his fellowship at the Cavendish Laboratory in Cambridge, working under J.J. Thomson, the discoverer of the electron and one of the most powerful figures in British physics. Cambridge was the centre of experimental physics. Thomson was a giant in the field, and Bohr arrived in September 1911 with ambitions of making his mark. He brought with him a copy of his doctoral thesis and ideas for how Thomson's electron theory could be improved. The reality proved bitterly disappointing. Thomson was polite but distant, preoccupied with his own research and administrative responsibilities as Cavendish professor and head of Trinity College. The great man had little interest in the theoretical speculations that Bohr wanted to discuss, and even less interest in corrections to his own electron theory that Bohr had worked out in his thesis. Within weeks, Bohr realized that Cambridge was the wrong place for him. Thomson worked in a different mode, focused on experiment and resistant to theoretical challenges from young unknowns. Bohr's careful critiques of Thomson's mathematical treatment of electron behavior in metals were not welcomed. They were in fact seen as presumptuous from a newcomer who had just arrived from provincial Copenhagen. When Bohr attempted to explain that Thomson's theory contained mathematical errors that affected its predictions, Thomson responded with icy courtesy that suggested the conversation was unwelcome. The British academic hierarchy was rigid in ways that Danish academic life was not. One did not contradict a professor, certainly not one of Thomson's stature, and absolutely not as a visiting foreign student barely past his doctorate. Bohr felt isolated and uncertain. His English was poor, heavily accented, delivered in the slow, circuitous manner that would characterize his speaking throughout his life. He would begin sentences without clear destination, modify them mid-course, append qualifications and subclauses until his meaning became obscured. This style worked in Danish conversations with patient interlocutors who would wait for his point to emerge. It did not work in Cambridge, where conversation was rapid, witty, performed. He attended seminars where the discussion moved too quickly for him to follow, where his attempts to ask questions were met with barely concealed impatience. The social aspects of Cambridge were equally alien. The formal dinners at Trinity College, with their elaborate rituals and hierarchies, made him uncomfortable. The assumption that everyone shared background in classics and British literature left him feeling ignorant. He had travelled to the supposed centre of physics only to discover he didn't fit. The Cambridge autumn was grey and damp. Bohr walked along the Cam, watching students punt past, feeling profoundly alone. He wrote letters to Margrethe Nørlund, to whom he had recently become engaged, describing his frustrations, his doubts about whether he had chosen the right career, his sense that he was wasting the precious fellowship time. Margrethe responded with encouragement, reminding him that the year was long, that Cambridge was not the only institution he could visit, that his work had value even if Thomson didn't appreciate it. Her letters became his lifeline, the one source of emotional support in an otherwise bleak period. Then came an invitation that changed everything. Ernest Rutherford, a New Zealander working at the University of Manchester, had heard about the young Danish physicist through scientific networks. Rutherford had read Bohr's published papers and found them interesting, even if he disagreed with some conclusions. He extended an invitation to visit Manchester during the Christmas break, to tour the laboratory and discuss physics. Bohr accepted eagerly, desperate for any relief from the Cambridge isolation. He travelled to Manchester in December 1911 and immediately felt the difference. Rutherford represented everything Thomson was not: boisterous, informal, enthusiastic, willing to engage with anyone who had interesting ideas regardless of rank or nationality. Rutherford's laboratory crackled with energy. Conversations happened at high volume, often several simultaneously. Ideas were thrown around, challenged, defended, discarded if they failed, pursued relentlessly if they showed promise. The atmosphere was egalitarian in a way Cambridge was not. A good idea from a student received the same attention as one from a professor. Rutherford himself embodied a kind of physics that Bohr had never encountered: forceful, intuitive, grounded in experimental results, but willing to speculate wildly about their meaning. And Rutherford had recently made a discovery that would define the next century of physics: the atomic nucleus. In 1911, based on experiments where alpha particles were fired at thin gold foil, Rutherford had concluded that atoms consisted of a tiny, dense, positively charged nucleus surrounded by a cloud of electrons. The experiments had been conducted by Hans Geiger and Ernest Marsden under Rutherford's direction. They had expected alpha particles, helium nuclei, positively charged and moving fast, to pass through gold foil with only slight deflections, like bullets through tissue paper. Most did, but a small fraction bounced backward as if they had hit something extremely dense. Rutherford later said it was as astonishing as if a naval shell had bounced off tissue paper and come back to hit you. This contradicted the prevailing plum pudding model, where charge was thought to be distributed evenly throughout the atom like raisins in pudding. Rutherford's nuclear model explained the experimental results beautifully. Most alpha particles passed through empty space between nuclei. A few came close to a nucleus and were deflected by its concentrated positive charge. The rare ones that scored direct hits bounced backward. The mathematics worked perfectly. The experimental evidence was overwhelming. The model was clearly correct. It also created an immediate, devastating problem. It was physically impossible according to known laws. If electrons orbited a nucleus like planets around a sun, electromagnetic theory demanded that they would constantly radiate energy. Accelerating charges radiate electromagnetic waves. This was a fundamental result of Maxwell's equations, one of the triumphs of 19th century physics. An electron in orbit is constantly accelerating toward the nucleus, so it should constantly radiate. Radiating energy means losing energy. An electron losing energy should spiral inward, faster and faster, collapsing into the nucleus within about a 10 billionth of a second. Atoms should not be stable, the universe should not exist. Yet here it was, existing anyway, filled with stable atoms that showed no sign of collapsing. Rutherford acknowledged this problem but shrugged it off as something to worry about later. He was an experimentalist with an experimentalist's priorities. The data was clear, the nuclear model explained it, therefore the model was right. Theory would have to catch up somehow. Theoretical problems were for theoretical physicists to solve. His job was to discover what nature did, not to explain why it did it. This attitude was frustrating to theoretically minded physicists but liberating for experimenters. It meant you could pursue evidence wherever it led without being constrained by existing theory. Bohr became obsessed with this paradox. He had come to England hoping to do useful work on electron theory. Instead, he had stumbled onto a crack in the foundation of physics itself. Classical electromagnetic theory, one of the great triumphs of 19th century physics, experimentally verified countless times, could not explain the most basic fact about matter, that it was stable. The problem consumed him. He returned to Cambridge after the Christmas break, but his heart was no longer in the work there. He spent his time reading everything about atomic structure, about spectroscopy, about the strange quantum hypothesis that Max Planck had proposed in 1900 to explain blackbody radiation. Planck's idea that energy came in discrete packets, quanta, rather than continuous waves, had been treated as a useful mathematical trick, not a fundamental truth about nature. Planck himself seemed to regard it as a computational convenience, hoping that a more classical explanation would eventually be found. Einstein had taken the quantum hypothesis more seriously in 1905, proposing that light itself came in quanta, photons, to explain the photoelectric effect. But even Einstein wasn't sure whether light quanta were real physical objects or just a way of describing energy transfer. But what if it was fundamental? What if the reason atoms didn't collapse was that electrons could only occupy certain discrete orbits and couldn't spiral inward because there was no intermediate state to spiral through? The idea felt simultaneously absurd and inevitable. Absurd because it meant abandoning continuous motion, one of the most basic assumptions of classical physics. Inevitable because nothing else could explain the stability of atoms. Bohr began working through the mathematics, exploring whether quantized orbits could be made consistent with spectroscopic data, trying to find principles that would determine which orbits were allowed. The pieces started fitting together in early 1912. Spectroscopy, the study of light emitted by heated elements, showed that each element produced characteristic patterns of bright lines at specific wavelengths. These spectral lines were like fingerprints, unique to each element. The patterns were mysterious but precise. For hydrogen, the simplest element, a Swiss schoolteacher named Johann Balmer had discovered in 1885 a mathematical formula that predicted the wavelengths of visible spectral lines with remarkable accuracy. The formula was purely empirical. Balmer had no idea why it worked, only that it did. Other series of hydrogen lines in the ultraviolet and infrared followed similar patterns. What if each spectral line corresponded to an electron jumping between specific allowed orbits? If the orbits had definite energies and an electron could jump from one orbit to another by emitting or absorbing light, then the light's energy would equal the energy difference between orbits. This would explain why spectral lines had discrete wavelengths. The wavelength depended on the energy difference, which was fixed by the orbit energies. It was a beautiful idea, elegant and simple. It was also completely ad hoc with no obvious theoretical justification. Bohr returned to Copenhagen in July 1912 with this problem haunting him. He had also acquired a wife, Margrethe Nørlund, whom he married in August of that year, immediately after returning from England. Margrethe came from an intellectual family herself. Her father had been a pharmacist, and her uncle was a mathematician. She had met Niels through family connections in Copenhagen's close-knit intellectual community. Their courtship had been conducted largely through letters during Niels's time in England, long detailed letters where he described his struggles with physics, and she responded with encouragement and practical advice. She was intelligent, patient, and willing to become Bohr's intellectual partner in ways that went beyond conventional marriage. She understood that she was marrying not just a man, but a mission, that Niels's work would always compete with family for his attention, that her role would be to create the conditions in which his genius could flourish. This sounds subordinate, and in some ways it was. The marriage reflected the gender assumptions of its era. But Margrethe was not merely passive. In the years ahead, Niels would dictate virtually all his papers to her, working through his ideas in long sessions where she would question, challenge, and help him clarify his thinking. She learned enough physics to engage meaningfully with his work, to recognize when his explanations were becoming murky, to push him toward greater clarity. She possessed the emotional stability that he increasingly relied upon as his ideas became more controversial. Niels had a tendency toward melancholy, toward becoming lost in thought to the point of neglecting practical matters, toward obsessing over problems until he exhausted himself. Margrethe grounded him, managed the household, dealt with correspondence and appointments, created a space where he could work without distraction. The marriage would last 50 years and produce 6 sons, but from the beginning it had an unusual character. Margrethe saw herself as partnering in Niels's mission, and that mission was to understand the atom. He worked through the winter of 1912 and into 1913, developing his model. The work was intense, consuming. He would spend entire days at his desk, filling page after page with calculations, trying different approaches, discarding false starts, gradually building toward a coherent theory. The mathematics was relatively simple, basic algebra, and some calculus, but the conceptual leap was enormous. He was proposing to overturn the principle of continuous motion that had governed physics since Newton, replacing it with quantum jumps between discrete states. He was saying that classical electromagnetic theory, validated by thousands of experiments, simply didn't apply at atomic scales. He was inventing rules, quantization conditions, that had no obvious justification except that they produced results matching experimental data. Bohr proposed that electrons could only occupy certain allowed orbits around the nucleus, orbits where the angular momentum was a multiple of Planck's constant divided by 2 pi. This condition was arbitrary in the sense that Bohr couldn't derive it from deeper principles. He simply asserted it because it worked. In these allowed orbits, electrons would not radiate energy. They simply stayed there, defying classical electromagnetic theory. This was the crucial revolutionary step, declaring that classical physics didn't apply, that electrons in allowed orbits simply obeyed different rules. An electron could jump from one orbit to another, and when it did, it would emit or absorb a photon of light with energy exactly equal to the difference between the orbit energies. This explained atomic spectra, the distinct lines of light that elements emitted when heated. Each line corresponded to an electron jumping between specific orbits. For hydrogen, with one electron, the calculations were straightforward. Bohr computed the energies of all the allowed orbits and then calculated the energy differences. When he compared these energy differences to the wavelengths of hydrogen's spectral lines, using Einstein's relation that a photon's energy equals Planck's constant times its frequency, the agreement was perfect. The Balmer formula, mysterious for 30 years, emerged naturally from the quantum orbit theory. The model predicted not just the visible lines but also the ultraviolet and infrared series that had been discovered more recently. It predicted the ionization energy of hydrogen, how much energy was needed to remove the electron entirely. Every prediction matched experimental measurements with stunning precision. The model was ad hoc, rule-based rather than derived from deeper principles. It violated cherished ideas about how nature worked. It combined classical orbit mechanics with quantum jumps in a way that was logically inconsistent. Electrons obeyed classical mechanics while in an orbit, but then jumped discontinuously to another orbit without occupying intermediate positions. And it fit the experimental data with stunning precision. Bohr had achieved what theorists dream of, a simple model that explained previously mysterious phenomena and made predictions that could be tested. Whether the model was true in some deeper sense was secondary. It worked, and it worked beautifully. Bohr wrote his model up in 3 papers and submitted them to the Philosophical Magazine, a leading British physics journal, in 1913. The papers were extraordinary not just for their physics but for their tone. Bohr wrote with unusual humility for a revolutionary, acknowledging the problems with his approach, noting that he couldn't explain why these rules held, only that they seemed to. He called it a preliminary approach, a scaffolding that might eventually be replaced by something more fundamental. This humility was genuine. Bohr truly saw his model as incomplete, as a stepping stone toward a deeper understanding that he couldn't yet glimpse. He recognized the logical inconsistencies, the arbitrary rules, the lack of a coherent theoretical foundation. But he also recognized that the model captured something true about atoms, that its empirical success couldn't be dismissed as coincidence. This humility also made the papers more difficult to dismiss as the ravings of a crank. Here was a young physicist proposing to overturn classical physics, but doing so with such evident, careful thought, such awareness of the problems with his approach, such detailed comparison with experimental data, that his ideas demanded serious consideration. He wasn't claiming to have solved everything. He was presenting a puzzle piece that seemed to fit, while acknowledging that the full puzzle remained mysterious. The physics community's response was mixed and evolved over time. Some, like Einstein, immediately recognized that Bohr had made a crucial breakthrough, even if the theoretical foundations were murky. Einstein wrote to a colleague that Bohr's work was an enormous achievement and one of the greatest discoveries. Rutherford was enthusiastic, recognizing that Bohr had solved the stability problem that plagued the nuclear model. But others were deeply skeptical. How could electrons just not radiate in certain orbits? What physical mechanism prevented it? Bohr had no answer except, this is what the data requires. To many classically trained physicists, this seemed like giving up on understanding, like replacing physics with numerology. The German physics community was particularly resistant. Max von Laue, who would later win the Nobel Prize for X-ray diffraction, dismissed Bohr's model as absurd and predicted it would be forgotten within a year. Arnold Sommerfeld, one of Germany's leading theoretical physicists, was initially skeptical but gradually came around as he found ways to extend and modify Bohr's model. The controversy was not merely scientific, but philosophical. Bohr's model represented a fundamental challenge to the idea that physics should be visualizable, mechanical, based on pictures of how things moved. It suggested that atomic physics might require abandoning such pictures in favor of abstract rules connecting observations. The next decade would prove Bohr correct in ways he hadn't anticipated. His model worked perfectly for hydrogen, explained some features of more complex atoms, and opened up an entirely new way of thinking about atomic structure. But it also became clear that the Bohr model was not the final answer. For atoms with more than one electron, the model's predictions became increasingly inaccurate. It couldn't explain why some spectral lines were brighter than others, or why certain transitions seemed forbidden, or the detailed structure of spectral lines when atoms were placed in magnetic fields. The model was a hybrid creature combining classical orbits with quantum jumps, an inconsistent theory that nonetheless captured something true about nature. Other physicists began building on it, extending it, finding its limits. Arnold Sommerfeld added elliptical orbits and relativistic corrections, improving agreement with experimental data for some atoms while making the theory more complicated. The correspondence principle emerged from Bohr's work, the idea that quantum mechanics must reduce to classical mechanics at large scales, that the new physics must contain the old physics as a special case. This principle became methodologically crucial, a guide for developing further theories. If a quantum theory didn't reduce to classical physics in the appropriate limit, it was probably wrong. But the most important consequence of Bohr's atomic model was psychological. It demonstrated that nature at the atomic scale did not obey the rules that governed the human-scale world, and that understanding nature might require abandoning intuitions built from everyday experience. This was a profound shift. Previous physics had always involved extending familiar concepts, forces, motions, energies, to new domains. Bohr was suggesting that atomic physics required fundamentally new concepts, that the quantum realm was not just smaller than the everyday world, but qualitatively different from it. By 1916, Bohr had returned to the University of Copenhagen as a professor of theoretical physics, having spent several years working in Manchester with Rutherford before accepting the Copenhagen position. Denmark during World War I maintained neutrality, which meant that while the rest of Europe tore itself apart, Danish scientific life continued relatively normally. The war disrupted communication between scientists in Allied and Central Powers countries, severing collaborations and creating bitter divisions. But Denmark, neutral and small, could maintain contacts with both sides. Bohr corresponded with physicists in Germany and Britain, sharing ideas, maintaining the internationalism of science despite the nationalist madness engulfing Europe. He watched the war with horror and incomprehension. The nations that had produced Goethe and Shakespeare were slaughtering each other in trenches. The civilization that had given birth to modern science was destroying itself with technology. The international community of scholars that Bohr believed in was fracturing along national lines, with scientists on both sides producing propaganda and working on weapons. German chemists developed poison gas. British physicists worked on submarine detection. The notion that science transcended politics seemed naive in the face of this catastrophe. Yet Bohr clung to it, believing that after the war, scientific internationalism could be rebuilt, that the common pursuit of truth could unite what politics divided. Bohr used Denmark's neutrality and his growing reputation to build something lasting. He attracted students, gave lectures, and began planning something more ambitious, an institute dedicated to theoretical physics, a place where scientists from different nations could gather to pursue understanding free from political constraints. The Carlsberg Foundation, funded by the famous brewery and dedicated to supporting Danish science and culture, agreed to finance the construction of a building that would house what became the Institute for Theoretical Physics. It opened in 1921 with Bohr as its director, and from that point forward it became known as the Copenhagen Institute, or simply Copenhagen, a name that would become synonymous with the center of the quantum revolution. The Institute's physical structure was modest compared to major laboratories in Britain or Germany, a 3-story building with offices, a small library, a lecture hall, and living quarters for visiting scientists. The library was lined with bookshelves holding the latest physics journals from around the world. The lecture hall had a blackboard that covered an entire wall, where discussions could sprawl across hours without running out of space. The living quarters were simple but comfortable, allowing foreign visitors to stay for weeks or months without financial burden. The building occupied a plot on Blegdamsvej in a quiet neighborhood away from the city center, surrounded by a garden where physicists could walk while discussing ideas. But the Institute's atmosphere was unique, more important than its physical facilities. Bohr created an environment of radical intellectual democracy where ideas mattered more than rank, where young physicists could challenge established figures, where clarity of thought was the only currency. Seminars were intense, freewheeling, often conducted in a mixture of languages as scientists from across Europe gathered. German, English, Danish, sometimes French, frequently all four in the same discussion as speakers, shifted languages mid-sentence to find the right word. Bohr himself presided over discussions with a distinctive style. He spoke slowly, softly, often pausing mid-sentence as he worked through an idea, sometimes asking a question that would redirect the entire conversation. His questions were rarely simple requests for information. They were invitations to think more deeply, to examine assumptions, to consider alternative interpretations. But what do you mean by? It was a favorite opening. What do you mean by position? What do you mean by measurement? What do you mean by knowing? The questions seemed pedantic until you tried to answer them and realized you didn't know what you meant, that the concepts you had used casually were actually profoundly unclear. This Socratic method could be exhausting, could make a 30-minute seminar stretch into a 3-hour marathon as Bohr probed every assumption, questioned every step, demanded clarity where none existed. Colleagues learned that working with Bohr required patience and stamina. He would continue discussions for hours, returning repeatedly to the same points, not satisfied until every participant understood the issue the same way he did. He would dictate papers to Margrethe or to assistants, speaking slowly, modifying sentences as he spoke, sometimes spending an entire afternoon on a single paragraph. The process was maddening but productive. What emerged from these endless revisions was prose of unusual precision, where every word was chosen carefully, where ambiguity was minimized, where the difficulty of the subject matter was confronted rather than hidden. But this relentless pursuit of shared understanding produced extraordinary results. The 1920s saw the Copenhagen Institute become the world center of quantum physics, attracting the brightest young physicists from across Europe and America. Werner Heisenberg arrived in 1924, a brilliant 22-year-old German who had just completed his doctorate and was already making waves with radical ideas. He and Bohr formed an intense working relationship, collaborating on problems, arguing about interpretations, pushing each other toward new insights. Heisenberg would develop matrix mechanics, the first complete mathematical formulation of quantum theory, during a stay on the island of Helgoland in 1925, inspired by conversations in Copenhagen. Wolfgang Pauli came from Hamburg, bringing his exclusion principle that explained the structure of the periodic table and his devastating critical ability. Pauli was famous for declaring theories not even wrong when they were too vague to be testable. Paul Dirac visited from Cambridge, a quiet Englishman who spoke so sparingly that colleagues joked about measuring silence in units of 1 Dirac. Dirac would develop his equation combining quantum mechanics and relativity, an equation so beautiful that it predicted the existence of antimatter before antimatter was discovered. Erwin Schrödinger passed through, though his wave mechanics approach clashed with Heisenberg's matrix formulation, and his philosophical views clashed with Bohr's Copenhagen interpretation. What emerged from these interactions was not a single theory, but a cluster of related formulations, all attempting to describe the quantum realm, all producing the same predictions despite using different mathematics. Heisenberg's matrix mechanics treated physical quantities as matrices that didn't commute. Position times momentum wasn't the same as momentum times position. Schrödinger's wave mechanics described particles as wave functions evolving in time according to a wave equation. Dirac's formulation used abstract state vectors in Hilbert space. The mathematics looked completely different, but the predictions agreed. This was both reassuring, the theories were clearly capturing something real about nature, and puzzling. If different mathematical formulations gave the same results, what was the physical reality underlying the mathematics? The puzzle was, what did these theories mean? What were they saying about the nature of reality? Bohr wrestled with this question obsessively. Unlike many physicists who were content to use quantum mechanics as a calculational tool, plug in numbers, get predictions, don't worry about interpretation, Bohr needed to understand its conceptual foundations. What did it mean that you couldn't simultaneously measure position and momentum with arbitrary precision? What did it mean that particles were described by wave functions? What did it mean that measurement seemed to play a fundamental role in the theory that you got different results depending on what you chose to measure? He developed what he called the principle of complementarity, first presented at a conference in Como, Italy, in September 1927 to commemorate the 100th anniversary of the death of Alessandro Volta. The lecture hall was packed with physicists from across Europe. Bohr spoke for over an hour, slowly, carefully, in his accented English, explaining an idea that he had been developing for months. The core idea was that quantum systems could be described in multiple, mutually exclusive ways, as particles or as waves with definite position or with definite momentum, and that both descriptions were necessary for complete understanding, even though they couldn't be applied simultaneously. An electron was not really a particle or really a wave, it was something for which human language and concepts were inadequate, and the particle and wave descriptions were complementary perspectives on a deeper reality that couldn't be directly visualized. Which description applied depended on the experimental setup, on what you chose to measure. If you set up an experiment to observe wave properties, you would see wave behavior. If you set up an experiment to observe particle properties, you would see particle behavior. You couldn't see both simultaneously because the experimental arrangements were mutually exclusive. An apparatus designed to observe wave interference destroyed the possibility of tracking particle trajectories, and vice versa. This was more than physics, it was epistemology, a claim about the limits of human knowledge. Bohr argued that the observer was inseparable from the observed in quantum mechanics, that the act of measurement fundamentally affected the system being measured, and that this wasn't a technical problem to be solved, but a basic feature of nature. We could not stand outside nature and observe it objectively. We were part of nature, and our observations were interactions that shaped what we observed. The classical ideal of a detached observer measuring an objective reality, independent of observation, was an approximation that worked at macroscopic scales but broke down at atomic scales. This philosophical depth made complementarity both profound and maddeningly vague. What exactly did it mean? Bohr spent decades trying to clarify it, writing papers and giving lectures that explored the principle from different angles. But he never achieved the kind of mathematical precision that would satisfy skeptics. Complementarity remained more a philosophical stance than a rigorous theory, a guide for thinking about quantum phenomena rather than a calculational tool. Some physicists found it illuminating, others found it obscure. But it became central to what was called the Copenhagen interpretation of quantum mechanics, the mainstream view of how to understand the theory's meaning. Not everyone accepted this view. In fact, one person rejected it completely and would spend the next 3 decades trying to prove Bohr wrong: Albert Einstein. The clash between Bohr and Einstein began at the Solvay Conference in Brussels in October 1927, a gathering of the greatest physicists in the world, funded by Belgian industrialist Ernest Solvay, to promote scientific discussion. The 5th Solvay Conference focused on quantum mechanics, bringing together Bohr, Einstein, Heisenberg, Schrödinger, Pauli, Dirac, Max Born, and other architects of the quantum revolution. Einstein had been instrumental in founding quantum theory. His work on the photoelectric effect had demonstrated the reality of light quanta, earning him the Nobel Prize. His theory of relativity had revolutionized our understanding of space and time. He was perhaps the most famous scientist in the world, a figure of mythic stature. But he had become increasingly disturbed by the direction quantum mechanics was taking. The Copenhagen interpretation, as Bohr's view came to be called, embraced probability as fundamental. It claimed that before measurement, a quantum system didn't have definite properties, only probabilities of different outcomes. This meant that physical reality was inherently indeterminate, that nature at its deepest level was ruled by chance rather than deterministic law. Einstein found this philosophically repugnant. He believed in an objective reality that existed independent of observation, a reality governed by deterministic laws that science's job was to discover. The notion that nature was fundamentally probabilistic, that God played dice with the universe, violated his deepest intuitions about how reality should be structured. He couldn't accept that physics had reached its limit, that it could only predict probabilities rather than definite outcomes, that it couldn't describe what was really happening between measurements. At the Solvay conference, Einstein presented a series of thought experiments designed to show that quantum mechanics was either incomplete or inconsistent. One involved a photon passing through a slit in a screen. Quantum mechanics predicted that you couldn't know both when the photon passed through and how much momentum it transferred to the screen. But Einstein designed a clever scenario where the screen was mounted on springs so you could measure the recoil, seemingly allowing simultaneous measurement of time and momentum with arbitrary precision, violating the uncertainty principle. Bohr defended the Copenhagen interpretation, working through Einstein's challenge overnight, showing how the uncertainty principle for the screen's own position and momentum prevented the simultaneous measurement Einstein proposed. The apparatus you needed to measure the timing precisely prevented you from measuring momentum transfer precisely, and vice versa. The debate was intense but friendly. Both men respected each other enormously despite their disagreement. Einstein admired Bohr's intellectual honesty and depth of thought. Bohr admired Einstein's physical intuition and philosophical seriousness, but they could not convince each other. Each day, Einstein would present a new thought experiment over breakfast. Each evening, Bohr would present a refutation. The younger physicists watched in fascination as two giants battled over the foundations of physical reality. And the debate continued for years beyond the Solvay conference. Einstein would propose a clever scenario that seemed to violate the uncertainty principle or allow faster-than-light communication. Bohr would think it through, sometimes for days, and find the subtle flaw in Einstein's reasoning. The exchanges were profound because both men were arguing from deep physical intuition, not just mathematical formalism. Einstein believed physics should describe an objective reality existing independently of observation. Bohr believed physics could only describe what we could say about reality based on measurements, that questions about reality, independent of measurement, were metaphysical rather than physical. The difference wasn't technical, it was philosophical, touching on questions about the nature of reality, knowledge, and the human relationship to nature. The debate reached its climax with the EPR paper in 1935, where Einstein and colleagues Boris Podolsky and Nathan Rosen presented what they thought was a definitive proof that quantum mechanics was incomplete. They described a situation where two particles were created in an entangled state, then separated by a large distance. Quantum mechanics predicted that measuring one particle would instantaneously affect the other, determining its properties even though the particles were far apart. This spooky action at a distance, as Einstein mockingly called it, seemed to violate the principle of locality, the idea that objects can only be directly influenced by their immediate surroundings. Either quantum mechanics allowed faster-than-light effects which violated relativity, or it was missing something, some hidden variables that would restore determinism and locality. Bohr's response took months to formulate and filled many pages, arguing that the EPR scenario didn't actually allow faster-than-light communication because the correlations only became apparent when comparing measurement results, which required conventional slower-than-light communication. The measurements on the distant particles were correlated but neither influenced the other causally. What appeared as faster-than-light influence was actually a misunderstanding of what measurement meant in quantum mechanics. The argument was subtle, perhaps too subtle, and didn't fully satisfy even some of Bohr's supporters. The debate would remain unresolved during both men's lifetimes. Decades later, in the 1960s and beyond, experiments based on Bell's inequality would test whether Einstein's hoped-for hidden variables could exist. The experiments showed that quantum mechanics was correct, and Einstein was wrong about reality being deterministic in the way he hoped, though in a deeper sense, Einstein's concerns about the incompleteness of the theory remain philosophically troubling to this day. Quantum mechanics predicts correlations that no local hidden variable theory can explain, vindicating Bohr's interpretation. But whether this means reality is fundamentally indeterminate or merely that our understanding is incomplete remains contested. But while Bohr was engaged in these abstract debates about the meaning of quantum mechanics, his personal life suffered a blow that would shadow the rest of his years. In 1934, his eldest son Christian died in a sailing accident at age 19. Christian had been a bright, athletic young man, studying medicine, seemingly destined for a successful life following in the family tradition of science and scholarship. He resembled his grandfather Christian Bohr in temperament and interests, combining intellectual ability with practical skill, equally comfortable in laboratory and outdoors. On July 10, 1934, during a sailing trip with friends off the coast near Tisvilde, the same beach town where Niels had spent summers as a child, where he had sailed with his own brother Harald, the boat capsized in a sudden squall. The weather had been calm, then changed rapidly as often happened on the Baltic. The boat went over, Christian, tangled in lines or struck by the boom, drowned within sight of shore, while friends tried desperately to save him. His body was recovered later that day. Niels, who had been at the Institute when he received the news, collapsed when told. Colleagues who had never seen him show strong emotion watched him break down completely, sobbing uncontrollably, repeating, "My boy, my boy." The funeral was private, family only, but word spread through the physics community. Letters of condolence arrived from around the world, from Einstein and Rutherford, and former students expressing shock and sympathy. Margrethe, who had lost her firstborn, had to manage not only her own grief, but her husband's. For months afterward, Bohr barely spoke about Christian. He returned to work quickly, perhaps too quickly, throwing himself into physics as if work could somehow compensate for grief. It couldn't, but it provided distraction, a focus for thought that wasn't the unbearable loss. Friends noticed that something had changed in Bohr after 1934. He had always been serious, but now there was a sadness underneath, a recognition of fragility that hadn't been there before, an awareness that the universe was not just quantum mechanical in its randomness, but personally tragic in ways that no theory could explain or ease. The loss affected his relationship with his other sons. He became more protective, more anxious about their safety, more insistent on knowing their whereabouts. He had always been an affectionate father despite his consuming work, spending time with his sons when he could, teaching them to sail, the same activity that had now killed one of them. After Christian's death, he couldn't bring himself to sail for several years. The summer house at Tisvilde, once a place of joy, became haunted by memory. Margrethe, who had lost a son, now also had to manage a husband who was trying to outwork his pain. She did so with characteristic quiet strength, holding the family together while managing her own grief, but the loss marked them both permanently. Physics itself was changing in the 1930s, shifting focus from the quantum mechanics of atoms to nuclear physics, the study of the nucleus itself. Bohr contributed crucial insights here too, transitioning from the physics of atomic electrons to the physics of the nucleus with characteristic thoroughness. In 1936, he proposed the liquid drop model of the nucleus, treating it not as a collection of individual protons and neutrons, but as a droplet of nuclear fluid that could oscillate and deform. The model was simple but powerful, explaining why nuclei of certain sizes were more stable than others, predicting how nuclei would behave when bombarded with particles, providing a framework for understanding nuclear reactions. This model helped explain nuclear reactions and would prove crucial for understanding nuclear fission when that phenomenon was discovered 3 years later. But Bohr's involvement with nuclear physics was about to take a darker turn that would overshadow all his previous work. In January 1939, he received word from Germany that Otto Hahn and Fritz Strassmann had split a uranium nucleus by bombarding it with neutrons, releasing enormous energy. The phenomenon was called fission, and its discovery would change the world. Bohr immediately understood the implications. He was scheduled to travel to the United States for a conference at Princeton and brought the news of fission with him. On the ship crossing the Atlantic in January 1939, he discussed the discovery with his assistant, Leon Rosenfeld. They worked through the physics, calculating energies, considering mechanisms. When they arrived in America and Bohr announced the discovery at the Princeton conference, American physicists, including Enrico Fermi, immediately began investigating whether a chain reaction was possible, whether splitting one nucleus could release neutrons that would split others, creating a self-sustaining reaction that could release energy on a massive scale. The possibility was obvious to anyone who understood the physics. Each uranium nucleus that split released 2 or 3 neutrons. If even one of those neutrons caused another fission, the reaction would sustain itself. If more than one caused fission, the reaction would grow exponentially, releasing enormous energy in a short time. The energy from splitting a single nucleus was about 200 million electron volts, more than 1 million times the energy from a chemical reaction like burning coal. If you could split all the nuclei in a kilogram of uranium nearly simultaneously, you would release energy equivalent to 20,000 tons of TNT. The bomb was theoretically possible the moment fission was discovered, obvious to any competent physicist who thought about it for an hour. Bohr worked with John Archibald Wheeler, a brilliant young American physicist, to develop a theory of fission, published in 1939. The paper explained the process in detail using the liquid drop model. The nucleus absorbed a neutron, became unstable, oscillated like a vibrating droplet, and eventually split into 2 smaller nuclei. They calculated that uranium-235, a rare isotope making up less than 1% of natural uranium, would fission with slow neutrons while the more common uranium-238 would not. This was a crucial insight with enormous implications. Creating a chain reaction would require either separating the isotopes, separating U-235 from U-238, or using a different fissile material like plutonium, which didn't exist in nature but could be created in a nuclear reactor. The paper was purely scientific, published in the Physical Review for the scientific community to read, but its implications were obvious to anyone paying attention. An atomic bomb was theoretically possible. Bohr recognized this, but he also believed, perhaps naively, that the technical difficulties of separating isotopes or producing plutonium were so immense that such a weapon couldn't be built for decades. Uranium-235 and uranium-238 are chemically identical, differing only in mass by about 1%. Separating them would require processing tons of uranium to produce kilograms of U-235. using techniques that didn't yet exist at industrial scale. Producing plutonium would require building nuclear reactors, also technology that existed only in theory. He was wrong about the timeline, though his error was understandable. What he couldn't know was that governments, particularly the American and British governments, were about to devote enormous resources to solving exactly these technical problems. When you can spend billions of dollars and employ hundreds of thousands of people, engineering challenges that seem insurmountable to academic physicists become solvable in a few years. Meanwhile, the political situation in Europe was deteriorating catastrophically. Germany had annexed Austria in March 1938, then Czechoslovakia in September. In September 1939, Germany invaded Poland, triggering World War II as Britain and France declared war on Germany. Denmark's position was precarious, a small, neutral country bordering Germany, militarily weak, dependent on German trade, hoping desperately that neutrality would be respected as it had been in World War I. That hope was naive. In April 1940, German forces simply marched into Denmark, occupying the country with minimal resistance in an operation that took less than a day. The Danish government chose collaboration over destruction, maintaining formal sovereignty while accepting German military control. Danish institutions continued functioning, the king remained in Copenhagen, the parliament continued meeting, but ultimate authority rested with German military commanders. For Bohr, this created an impossible situation. He was a Dane, deeply loyal to his country, unwilling to abandon Copenhagen, while Danish sovereignty nominally continued. He was also partly Jewish through his mother, though not religious and not particularly identified with Jewish culture. Under Nazi racial laws, this Jewish heritage made him suspect and potentially vulnerable, though Denmark's collaborative arrangement initially protected Danish Jews from the persecution occurring in Germany and occupied territories. He was a figure of international scientific prominence with contacts throughout the Allied world, which made German authorities view him as a potential security risk. And he was the head of an institute that included Jewish scientists and anti-Nazi Germans who had fled to Denmark. The institute became a kind of sanctuary, protected somewhat by Bohr's stature and the Danish government's semi-independence. But it was a fragile protection that could collapse at any moment. For 3 years, from April 1940 to September 1943, Bohr tried to maintain normal scientific work under occupation. He continued research, hosted seminars when possible, and protected his colleagues as much as possible. The institute became a refuge for scientists endangered by Nazi policies. James Franck, a German Nobel laureate who had left Germany in 1933, was in Copenhagen when the occupation began and stayed under Bohr's protection. George de Hevesy, a Hungarian chemist working at the institute, dissolved the gold Nobel Prize medals belonging to Franck and Max von Laue in acid to hide them from German authorities. The Nazis had forbidden German citizens from possessing Nobel medals after pacifist Karl von Ossietzky won the Peace Prize, and taking a medal out of Germany was illegal. The gold sat in an unmarked jar of acid on a shelf in the lab throughout the occupation, invisible to German inspectors, eventually recovered after the war and recast into medals. Bohr also engaged in subtle resistance, helping Jewish scientists escape when possible, maintaining contacts with Allied scientists despite censorship, using his position to shield dissidents. He was careful, never openly defiant, but persistent in protecting those under his authority. He met with German officials when required, speaking in his slow, circuitous manner that often left them uncertain what he had actually said, creating ambiguity he could later exploit. He maintained connections with Swedish colleagues who could help refugees escape across the narrow strait separating Denmark from neutral Sweden. The most mysterious episode of this period occurred in September 1941 when Werner Heisenberg visited Copenhagen. Heisenberg had been Bohr's close collaborator and friend in the 1920s, one of the architects of quantum mechanics, a regular visitor to the Copenhagen Institute. They had worked together, argued together, pushed each other toward understanding. Heisenberg was like a son to Bohr in some ways, intellectually if not personally. Now he was working for the German nuclear program, leading the theoretical effort to understand whether a German atomic bomb was feasible. The two met for a walk one evening through the streets of occupied Copenhagen, presumably to avoid electronic surveillance, though whether any existed is unclear. Something happened during that conversation that permanently damaged their relationship. Accounts differ wildly about what was said, complicated by the fact that neither man wrote down a clear contemporary account, and their later recollections contradicted each other and evolved over time. Heisenberg later claimed he was trying to convey that the German bomb project was not progressing well, and to learn if the Allies were pursuing one, perhaps to establish some kind of mutual understanding between physicists on both sides that the bomb should not be built. Bohr believed Heisenberg was either fishing for information to help the German program or seeking moral absolution for working on a Nazi weapon while claiming to oppose it. Bohr was deeply disturbed by the conversation, felt Heisenberg was being dishonest or self-deceiving, and essentially ended the friendship. They barely spoke again, and when they did it was formal and cold. This encounter haunted Bohr for the rest of his life. After the war, Heisenberg would write claiming he had tried to prevent both sides from developing atomic weapons, that he had deliberately slow-walked the German program, that his visit to Copenhagen had been an attempt at establishing physicist-to-physicist communication above politics. Bohr didn't believe this self-serving narrative. He drafted angry letters in response accusing Heisenberg of dishonesty, but never sent them, eventually burning the drafts because he couldn't formulate a response that satisfied him. The truth about what Heisenberg intended may never be known. He may not have known himself, may have been rationalizing his own choices, may have been genuinely conflicted, but for Bohr, the meeting represented a terrible corruption of the scientific internationalism he had spent decades building. Physics was supposed to transcend politics. The Institute was supposed to be neutral ground where ideas mattered more than nationality, where Germans and British and Americans and Russians could work together in pursuit of truth. Heisenberg's visit revealed that this ideal had become impossible. Science had been weaponized, and the weapons were being built by his friends and former students on both sides. The community he had created was being torn apart by forces he couldn't control, and there was nothing he could do to prevent it. By 1943, the situation in Denmark had become untenable, even for Bohr's protected position. The Danish government's collaboration strategy was collapsing as resistance activities increased and German demands became more severe. Sabotage attacks by the Danish resistance prompted German retaliation. In August 1943, the Danish government resigned rather than accede to German orders to suppress resistance and execute saboteurs. Germany imposed direct military rule, ending the fiction of Danish sovereignty. And German authorities began planning to round up Denmark's Jewish population for deportation to concentration camps. Werner Best, the German plenipotentiary in Denmark, informed Berlin that he intended to implement the final solution in Denmark, arresting and deporting the country's approximately 8,000 Jews. The operation was scheduled for October 1st and 2, 1943, during the Jewish New Year, when families would be gathered in their homes. But information about the planned roundup leaked, possibly deliberately from sympathetic German officials, possibly through Danish police intelligence. The Danish resistance and the Swedish government mounted a hurried rescue operation, smuggling Jews across the strait to Sweden in fishing boats and small craft. Bohr, as a prominent half-Jew and known Allied sympathizer, was in immediate danger. The resistance brought him warning that arrest was imminent, that he and his family needed to escape immediately. On the night of September 29, 1943, Bohr and his wife Margrethe received final warning. That night, They were taken by the resistance to a fishing boat waiting at a small harbour. Along with dozens of other refugees, they crossed the narrow strait to Sweden in darkness, evading German patrols. The crossing took several hours in cold autumn weather in an overcrowded boat that stank of fish. They arrived in Malmö, Sweden the next morning, exhausted, stateless, and uncertain what would come next. But Bohr couldn't simply stay in Sweden as a refugee waiting out the war. The British government, learning he had escaped, immediately arranged for his transport to England. They wanted him working on the Allied atomic bomb project. British intelligence knew that German physicists were working on nuclear fission, didn't know how far they had progressed, and desperately wanted Bohr's expertise. On October 6, 1943, he was taken to a military airfield and loaded into the bomb bay of a Mosquito bomber, a small, fast wooden aircraft used for high-altitude reconnaissance missions. The Mosquito couldn't carry passengers in the traditional sense. It was a two-man aircraft, pilot and navigator, with no passenger cabin. The bomb bay was the only space available, and it was barely large enough for a man to lie down. Bohr, a large man, had to curl awkwardly into the cramped metal space. He was given an oxygen mask and flight suit. The plane would fly at high altitude, where the temperature dropped below freezing and oxygen was necessary. The pilot briefed him. As they climbed, he must ensure the oxygen was flowing properly. If he felt dizzy or short of breath, he should use the intercom immediately to alert the crew. They took off into overcast skies and began climbing toward the flight altitude of around 25,000 feet, high enough to avoid German fighters and anti-aircraft fire. The Mosquito was fast and could outrun most fighters, but avoiding detection was safer than outrunning pursuit. The pilot, focused on navigation and watching for German aircraft, didn't notice that Bohr's mask wasn't sealing correctly over his large head. The mask had been designed for RAF crew members, not for a 58-year-old physicist with a head circumference at the upper end of human variation. Bohr, unfamiliar with aviation equipment and without the language facility to easily communicate technical problems in English, didn't realize he was being starved of oxygen until his vision began tunneling. Hypoxia is insidious. It doesn't announce itself with pain or clear symptoms, but with gradual cognitive impairment that makes it difficult to recognize what's happening. He felt tired, then confused. Then his vision narrowed. He tried to reach the intercom but couldn't coordinate his movements properly. His consciousness faded and he slumped unconscious in the bomb bay as the aircraft continued climbing. He survived because the flight was short, and the pilot descended after crossing the North Sea, reducing altitude as they approached Scotland. The descent increased oxygen availability enough that Bohr didn't die, though he remained unconscious. When the plane landed in Scotland and the bomb bay doors opened, ground crew found Bohr unconscious but alive, his face blue from hypoxia, barely breathing. He woke in a hospital bed with a splitting headache, alive only because his brain had survived approximately 18 minutes of severe oxygen deprivation without suffering irreversible damage. The doctors told him he had been extraordinarily lucky, that another few minutes would have meant either death or permanent brain damage severe enough to end his scientific career. Bohr, typically understated, reportedly said that it would have been a pity to have escaped the Nazis only to die in an Allied aircraft due to an ill-fitting oxygen mask. The incident became one of many dramatic stories about the war, repeated in various forms. But for Bohr it represented something deeper, the absurdity of a situation where a theoretical physicist was being smuggled across occupied Europe like contraband, where ideas about uranium isotopes were so valuable that governments would risk killing the man who held them rather than allow those ideas to fall into enemy hands. After recovering for several days, Bohr was taken to London and briefed on the Manhattan Project, the massive Allied effort to build an atomic bomb. What he learned shocked him. He had believed that the technical difficulties of isotope separation and plutonium production would delay any bomb project for at least a decade. He learned that the project was far more advanced than he had believed possible. The Americans had constructed enormous facilities at Oak Ridge, Tennessee for isotope separation using multiple techniques simultaneously. They had built nuclear reactors at Hanford, Washington for plutonium production. Theoretical work on bomb design was progressing at a secret laboratory in Los Alamos, New Mexico. The scale was staggering. Billions of dollars, hundreds of thousands of workers, entire cities built in secret. The project was far beyond anything Bohr had imagined possible, an industrial and scientific effort of unprecedented magnitude. The weapon he had thought was decades away was perhaps 2 years from reality. The Americans and British were convinced that Germany was pursuing a similar program, were terrified that Hitler might obtain nuclear weapons first, and were racing to build a bomb before Germany did. They wanted Bohr's expertise to help ensure the Allied bomb worked, and worked before any potential German bomb. He was asked to join the project, working first in England and then in the United States. Bohr agreed, but not enthusiastically. He understood why the Allies needed to develop the bomb before Germany did. The possibility of Hitler obtaining nuclear weapons was too horrible to contemplate, would mean global catastrophe, made working on an Allied bomb a necessity. But he was deeply troubled by what would happen after the war. If the United States successfully built atomic bombs and used them to end the war, what would prevent a nuclear arms race afterward? What would stop the Soviet Union from developing their own weapons? How could humanity avoid destroying itself with this new power? He traveled to the United States in December 1943, still recovering from his oxygen deprivation ordeal, and was taken to Los Alamos, New Mexico, where the bomb design work was centered. The project was led by Robert Oppenheimer, a theoretical physicist who had organized the best scientific minds in America to solve the technical problems of bomb construction. Los Alamos occupied a remote mesa top in the desert, isolated from population centers for security and safety, connected to the outside world by a single road. Scientists lived on site with their families in hastily constructed housing, worked in laboratories equipped with the latest equipment, and focused entirely on the bomb. Bohr arrived under the alias Nicholas Baker, a laughably transparent cover given that he was one of the most recognizable physicists in the world, with distinctive appearance and accent. Security officials insisted on the alias anyway. He was assigned to work on theoretical aspects of bomb design, particularly on questions about the critical mass of fissile material needed to sustain a chain reaction and the behavior of the bomb during the initial stages of explosion. His direct technical contributions were modest. At 58, he was older than most of the scientists there, and the specific engineering problems of bomb construction were not his specialty. The work required detailed calculations and familiarity with the properties of materials like plutonium that he didn't have. But his presence had symbolic weight. The father of atomic physics, the man whose model had first explained how atoms were structured, was now working to destroy them on a massive scale to release their energy. More importantly, Bohr became the project's conscience. He began having conversations with younger physicists about what would come after the war, about the moral implications of what they were building, about the political arrangements that would be necessary to prevent nuclear catastrophe. He argued that the atomic bomb changed everything, that international relations would need to be fundamentally restructured to prevent catastrophe. The old system of nation-states pursuing their own interests through diplomacy and war could not continue in a nuclear age. One miscalculation could destroy civilization. He believed that the solution was radical openness. The United States should immediately share atomic secrets with the Soviet Union and work toward international control of nuclear weapons through some new, global institution, perhaps under UN authority. This openness would build trust, prevent an arms race, and create the conditions for lasting peace. This was, even at the time, recognized as naive by hard-headed political realists. The wartime alliance with the Soviet Union was already fraying. Stalin was consolidating control over Eastern Europe, showing no interest in democratic governance or international oversight. The idea that Stalin would accept international inspections or constraints on Soviet sovereignty was fantasy. The Soviet Union had sacrificed millions to defeat Germany and had no intention of allowing Western powers to dictate terms. But Bohr persisted, believing that scientists had a moral obligation to advocate for policies that would prevent the catastrophic use of the technologies they had created. He arranged meetings with Churchill and Roosevelt, hoping to convince them to approach the Soviets about atomic cooperation before the war ended, before positions hardened, while cooperation might still be possible. Getting these meetings required pulling strings, using his scientific prestige, appealing to officials who understood the bomb's importance. Eventually, through persistence and the support of British officials who took him seriously, he secured meetings with both leaders. The meetings were disasters, though Bohr didn't fully realize it at the time. Churchill found Bohr incomprehensible, his slow, circuitous way of speaking, his tendency to qualify every statement, his philosophical digressions, all frustrated the Prime Minister, who wanted simple answers to simple questions. Churchill's science advisor, Frederick Lindemann, wrote afterward that Bohr's presentation had been muddled and unconvincing, that he had failed to make a clear case, that Churchill had been left baffled about what exactly Bohr was proposing. Bohr came away from the meeting believing he had made progress, that Churchill had at least understood the importance of approaching the Soviets before using the bomb. In fact, Churchill was so alarmed by Bohr's internationalism that he warned Roosevelt in a private communication that Bohr might be a Soviet sympathizer who should be watched, that his advocacy for sharing atomic secrets could be cover for espionage, that at minimum he was politically naive in ways that made him dangerous. The suggestion that Bohr was disloyal was absurd. He was one of the most thoroughly decent men in physics, motivated entirely by idealism. But to Churchill's hardened political sensibilities, Bohr's idealism looked like dangerous naivety at best, suspicious sympathy for communism at worst. The meeting with Roosevelt went somewhat better in tone. Roosevelt was polite, charming, seemed sympathetic to Bohr's concerns, but it produced no concrete action. Roosevelt agreed that post-war atomic policy was important, made vague statements about the need for international cooperation, and then did nothing. He had larger concerns: winning the war, managing the alliance with Stalin and Churchill, planning for post-war European reconstruction. Whether to share atomic secrets with the Soviets was a decision he would defer until circumstances forced it. Bohr left these meetings believing he had at least planted seeds, that the ideas would germinate, that policymakers would eventually act on them. He had no idea that Churchill had recommended he be placed under security surveillance as a potential security risk. The war in Europe ended in May 1945 with Germany's unconditional surrender. German nuclear program, it turned out, had never progressed beyond a small experimental reactor. Heisenberg's team had made crucial errors in their calculations and had never received the massive resources that would have been needed to build a bomb. The immediate justification for the Manhattan Project, preventing a Nazi atomic bomb, vanished. But the project continued because attention had shifted to Japan, which was still fighting despite catastrophic losses. Bohr was not directly involved in the decision to use atomic bombs on Japanese cities, but he knew it was being contemplated. Military planners were preparing for an invasion of the Japanese home islands, an operation that would cost hundreds of thousands of American casualties and potentially millions of Japanese deaths. The atomic bomb offered an alternative, demonstrate such overwhelming destructive power that Japan would surrender without invasion. But using the bomb would mean destroying cities and killing vast numbers of civilians, raising moral questions that Bohr found deeply troubling. He drafted memoranda arguing for a demonstration of the bomb's power rather than using it on cities, suggesting that a test witnessed by international observers might achieve the goal of forcing Japanese surrender without mass civilian casualties. These suggestions were noted and filed away. Military planners had different priorities: end the war quickly, minimize American casualties, demonstrate American power to the Soviet Union. A demonstration test might fail to detonate, wasting precious fissile material. A test over water or uninhabited land might not convince Japanese leadership of the weapon's destructive power. Better to use it on a real target, to show unmistakably what the bomb could do. On August 6, 1945, a uranium bomb destroyed Hiroshima, killing approximately 80,000 people immediately and tens of thousands more from radiation and injuries in the following months. 3 days later, a plutonium bomb destroyed Nagasaki, killing approximately 40,000 immediately. The war ended on August 15th with Japan's surrender. The nuclear age began, and Bohr's life's work, beginning with his quantum model of the atom in 1913, pursued through decades of fundamental research into atomic structure, had culminated in roughly 200,000 dead in seconds, cities erased, survivors carrying radiation injuries that would haunt them for life. He returned to Copenhagen in late 1945 to find his institute had survived the occupation largely intact, though several colleagues had not. Some had been arrested by German authorities, some had fled to Sweden or further, some had simply disappeared into the chaos of war's end. The city bore scars, buildings damaged by Allied bombing and German demolitions, population traumatized by 5 years of occupation, economy disrupted by wartime controls and destruction of infrastructure. But Denmark had been spared the wholesale destruction visited on Germany or Eastern Europe. The Soviet army had not fought through Denmark. The Allied bombing had been relatively limited. The infrastructure remained largely functional. Bohr was 60 years old, exhausted, and morally burdened by the realization that his quantum model of the atom, developed in the idealistic pursuit of knowledge 3 decades earlier, had led directly to weapons of unimaginable horror. Many scientists involved in the Manhattan Project dealt with this burden by returning to pure research, convincing themselves that they had been solving technical problems and bore no responsibility for how their solutions were used. Science was neutral, they argued. Politicians decided how to use it. Scientists couldn't be held accountable for political decisions. Bohr could not take this path intellectually or morally. He felt responsibility deeply, perhaps because his work had been so foundational. Without the understanding of atomic structure that began with his 1913 papers, none of the subsequent developments would have been possible. He had opened the door to the nucleus. Others had walked through it, but the door had been his. You could trace a direct line from the Bohr model to the understanding of isotopes, to the discovery of fission, to the atomic bomb. That line ran through his work, and he couldn't pretend otherwise. For the remainder of his life, 17 years from his return to Copenhagen until his death in 1962, Bohr became an activist for international control of atomic energy. He wrote open letters, gave speeches, met with politicians, and used his scientific prestige to advocate for the creation of international institutions that would prevent nuclear war. In 1950, he wrote an open letter to the United Nations calling for radical transparency between nations on atomic matters, arguing that only through openness could mutual trust be built and arms races prevented. The letter was eloquent, thoughtful, and completely ineffective. By 1950, the Cold War had solidified into the fundamental organizing principle of international politics. The Soviet Union had tested its first atomic bomb in August 1949, ending the American nuclear monopoly 4 years earlier than American intelligence had predicted. Both superpowers were racing to develop hydrogen bombs that would be thousands of times more powerful than the weapons used on Japan, bombs whose explosive power came from fusion rather than fission, bombs that could destroy entire metropolitan areas. The idea that either side would share nuclear secrets or submit to international control was absurd in this context. The United States saw its nuclear superiority as essential to deterring Soviet aggression. The Soviet Union saw nuclear weapons as essential to balancing American power and preventing American interference in Soviet interests. Neither side had any intention of allowing an international authority to constrain their nuclear programs. Trust was non-existent. Verification was impossible in closed Soviet society, and the stakes were too high for either side to risk the other cheating. Bohr's idealism, which had seemed merely naive in 1943, now seemed almost willfully blind to political reality. Yet he continued. He participated in the first Atoms for Peace conferences organized by the United Nations in the mid-1950s, which attempted to promote peaceful uses of nuclear energy, power generation, medicine, agriculture, while limiting weapons proliferation. He received the first Atoms for Peace Award in 1957, a recognition of his advocacy and his contributions to physics. The award came with substantial prize money and international recognition, acknowledging his role as a voice of scientific conscience. He wrote philosophical papers trying to explain why openness was necessary, drawing parallels to the complementarity principle in quantum mechanics. Just as you couldn't understand quantum systems without accepting their dual nature, you couldn't achieve security in the nuclear age without accepting transparency. The analogy was strained, and it convinced few policymakers, but it reflected Bohr's conviction that the lessons of quantum mechanics had broader implications for human affairs. If quantum mechanics taught that observation and observed were inseparable, perhaps politics should recognize that nations couldn't pursue security independently, but were bound together in common vulnerability. These arguments influenced a generation of scientists who shared his discomfort with nuclear weapons, but achieved limited concrete results in policy terms. The Pugwash conferences, bringing together scientists from East and West to discuss arms control, operated in the spirit Bohr had championed. The conferences began in 1957, bringing together scientists from both sides of the Cold War to discuss how scientific expertise could inform arms control. Bohr participated when health allowed, lending his prestige to the enterprise, but the conference's influence on actual policy remained marginal. Meanwhile, his scientific work continued, though at a reduced pace befitting his age and health. The Institute remained active, training new generations of physicists, hosting visitors from around the world, maintaining the tradition of international collaboration that Bohr had established. His son Arge joined him there, eventually becoming a nuclear physicist of distinction who would win his own Nobel Prize in 1975 for work on the structure of the atomic nucleus, extending in some ways the work his father had begun. Bohr's relationship with physics itself had become complicated in his final decades. The quantum mechanics he had helped create had been enormously successful, perhaps the most successful scientific theory ever devised in terms of empirical accuracy. It explained chemistry, atomic physics, nuclear physics, and increasingly solid-state physics and particle physics. Every test confirmed its predictions. Technologies based on quantum mechanics, transistors, lasers, nuclear reactors, were transforming society. Yet the interpretation, the question of what quantum mechanics meant about the nature of reality, remained disputed. Einstein had died in April 1955 without accepting the Copenhagen interpretation, still believing that quantum mechanics was incomplete, still hoping that a deeper deterministic theory would be found. His death removed Bohr's greatest intellectual antagonist, the person who had pushed him to clarify and defend complementarity, who had forced him to think more deeply about measurement and reality. Without Einstein, the debate about quantum foundations became less urgent to the physics community. New generations of physicists increasingly treated interpretive questions as irrelevant philosophy, focusing instead on calculations and predictions. Shut up and calculate became the pragmatic motto of a field that was making spectacular progress by ignoring the philosophical questions that Bohr considered central. This shift troubled him deeply. Bohr had always maintained that physics was not merely about prediction, but about understanding, that the goal was to comprehend what nature was telling us about reality, not just to manipulate equations to make predictions. The complementarity principle was an attempt to preserve this understanding in the face of quantum strangeness, to say something meaningful about what reality was like, even if it couldn't be visualized classically. But by the 1950s, many physicists regarded complementarity as overly philosophical, a relic of a more naive era when scientists thought they could visualize what was happening at the atomic scale. The new generation used quantum mechanics as a tool without worrying about what the tool meant. They calculated atomic energy levels, designed particle accelerators, predicted nuclear decay rates, all without concerning themselves with whether an electron was really a particle or a wave. The mathematics worked, the predictions matched experiment, and that was enough. Bohr found this deeply unsatisfying, this reduction of physics to mere instrumentalism, but he also recognized that he might be fighting a losing battle. Physics was becoming more mathematical, more specialized, more focused on increasingly abstract entities like quarks and gauge fields. The era when a single physicist could hope to understand all of fundamental physics as Bohr had understood it in the 1920s was ending. Science was fragmenting into subspecialties, each with its own technical language, its own concerns, its own culture. He also watched as the physics community itself changed structurally and culturally. The Copenhagen Institute, which had been the world center in the 1920s and 30s, was now one of many important centers. American institutions, flush with government funding in the wake of the Manhattan Project, had become dominant. The Soviet Union had built its own impressive physics establishment, largely closed to Western contact, but producing excellent work. CERN, the European Particle Physics Laboratory, was being constructed in Switzerland as a collaborative European project to compete with American dominance in high-energy physics. The informal, seminar-based approach that Bohr had pioneered was being replaced by large collaborative experiments involving dozens or hundreds of scientists, massive equipment like particle accelerators and bubble chambers, and formal organizational hierarchies. Physics was becoming industrialized, a transformation that was scientifically productive but culturally alien to Bohr's vision. He had imagined physics as a conversation among individuals pursuing truth, as an almost artistic enterprise where insight mattered more than resources. It was becoming a corporate enterprise pursuing funding, where success required managing large teams and securing government grants. Yet even in his 70s, he maintained intellectual vitality and engagement with new developments. He continued working on problems in nuclear physics, particularly on the collective model of the nucleus that his son, Argo, was developing, though he acknowledged that his best work was behind him. He gave lectures, mentored students when they sought him out, and engaged with new developments in particle physics even when they didn't align with his philosophical preferences. He remained convinced that the interpretation of quantum mechanics mattered, that the questions about measurement and reality that he and Einstein had debated were not settled despite what the pragmatists claimed. He wrote papers about the principle of complementarity as it might apply beyond physics, to biology, where you couldn't simultaneously describe an organism as a physical system and as a living entity, to psychology, where thoughts couldn't be simultaneously described in neurological and experiential terms. to the relationship between free will and determinism. These excursions into other fields were not always well received by specialists, who often felt that Bohr was overextending physics concepts beyond their domain of validity. But they reflected Bohr's conviction that the lessons of quantum mechanics had implications for how humans understood knowledge itself, that complementarity wasn't just about electrons, but about the fundamental human relationship to reality. His health began declining in the late 1950s. He had a heart attack in 1958 that forced him to reduce his activities dramatically. He could no longer work the long hours that had characterized his entire career. He tired more easily, needed rest in the afternoons, found sustained concentration difficult. He continued working, but more slowly, more carefully, aware that time was running out. There were papers he wanted to write, ideas he wanted to develop, younger physicists he wanted to influence. But the body was failing, betraying the still active mind. On the morning of November 18, 1962, he was at his desk in the honorary residence that Carlsberg had provided him decades earlier, working on a manuscript about complementarity and its philosophical implications. He felt tired and lay down for his customary midday rest. Margrethe checked on him an hour later and found him unconscious. She called for a doctor immediately, but by the time medical help arrived, Bohr had died. The cause was heart failure, the culmination of years of declining cardiac function. He was 77 years old, working on physics until the final day, trying to complete one more idea, clarify one more concept, contribute one more insight to the field he had helped revolutionize. The reaction to his death was global and immediate. Tributes came from scientists, institutions, and governments worldwide. He was recognized as one of the giants of 20th century physics, a figure whose work ranked with Einstein's for its fundamental importance to our understanding of nature. The institute was officially renamed the Niels Bohr Institute in his honor. UNESCO held memorial sessions. Scientific journals published special issues dedicated to his work and life. His collected works were eventually published in multiple volumes by the Danish Academy of Sciences, a comprehensive record of his scientific papers and correspondence. But the tributes also revealed something about how he was remembered and what was emphasized. He was celebrated primarily as the creator of the Bohr model and a founding father of quantum mechanics, as the architect of the Copenhagen interpretation, as a giant of early 20th century physics. His decades of work on nuclear physics received less emphasis. His philosophical writings on complementarity were noted but often treated as interesting sidebars rather than central contributions. And especially his activism on nuclear weapons control received minimal attention in the scientific tributes, perhaps because it was seen as political rather than scientific, perhaps because it had been largely unsuccessful. The narrative that formed was of a great scientist who had made crucial discoveries in his youth and then spent the rest of his career explaining and defending them. This narrative was not entirely false, but it missed essential aspects of who Bohr had been and what he had tried to accomplish. It reduced a complex life to a simple story of scientific triumph, when the actual life had been as much about struggle and failure as about success, about moral wrestling with the consequences of knowledge as much as about acquiring knowledge itself. What the simplified narrative obscured was the tragedy at the center of Bohr's life, a tragedy that went beyond personal losses like his son's death to encompass the entire trajectory of his career. He had been driven by the conviction that understanding nature was humanity's highest calling, that knowledge was inherently good, that the pursuit of truth transcended politics and nationalism. He had built an institution based on these principles, creating a space where scientists from different nations could collaborate in the shared project of understanding reality, where ideas mattered more than nationality, where the international community of science could serve as a model for international cooperation more broadly. And then he had watched as this knowledge became a weapon, as his colleagues, were divided by nationalism, as the understanding he had sought enabled destruction on an unprecedented scale. The Bohr model had started as an attempt to explain why atoms didn't collapse, to understand the stability of matter. It ended by enabling humanity to collapse atoms deliberately, to make them unstable, releasing enough energy to destroy cities and kill hundreds of thousands. This was not ironic in the literary sense. It was the central contradiction of 20th century science, the dark dialectic of knowledge and power, and Bohr lived it more completely than almost anyone. His response to this contradiction was to insist, against all evidence, that international cooperation was possible, that openness could replace secrecy, that scientists could influence political decisions through moral argument, that the catastrophe could be prevented through reason and goodwill. He failed. The nuclear arms race he feared came to pass exactly as he predicted. By the time of his death, the United States and Soviet Union had accumulated tens of thousands of nuclear weapons, had developed intercontinental ballistic missiles to deliver them, had come terrifyingly close to nuclear war during the Cuban Missile Crisis just weeks before he died. The institutions of international control he had envisioned existed only in vestigial form, ignored by the nations they were supposed to constrain. The United Nations had no real power over nuclear weapons. The Atomic Energy Commission proposals for international control had failed in the late 1940s. Treaties limiting testing or deployment were minimal and often violated. His idealism had proven inadequate to the realities of geopolitics, to the logic of nuclear deterrence, to the dynamics of great power competition. Yet he had persisted in advocating for cooperation and openness, not because he was naive about human nature. His philosophical work showed deep understanding of human limitations and the constraints on knowledge, but because the alternative was accepting that the knowledge he had devoted his life to pursuing would inevitably destroy the civilization that produced it. This was unacceptable to him morally and intellectually. Better to fight for a possible world, even if unlikely, than to accept catastrophe as inevitable. The debates he had with Einstein remain philosophically unresolved despite decades of experimental tests confirming quantum mechanics. Quantum mechanics has been confirmed in every conceivable way. Its predictions about entanglement and non-locality have been verified through experiments testing Bell's inequality. Einstein's hope for a deterministic reality beneath the quantum probabilities has not been vindicated. Local hidden variable theories have been ruled out experimentally. Yet Einstein's concerns about the interpretation of quantum mechanics resonate with many physicists even today. The measurement problem, what exactly happens during a quantum measurement, how definite outcomes emerge from quantum superpositions, still lacks consensus explanation. Alternative interpretations like the many worlds view, the de Broglie-Bohm pilot wave theory, and various collapse theories have gained adherents. The Copenhagen interpretation that Bohr championed is no longer dominant among working physicists, though it remains influential and is still taught as the standard interpretation in many textbooks. What has become clear is that the question Bohr and Einstein were arguing about, what does quantum mechanics tell us about the nature of reality, may not have a simple answer within physics itself, may in fact be undecidable empirically, may depend on philosophical commitments that go beyond experimental test. This would have troubled Bohr, who believed physics should provide understanding of nature, not just prediction of measurement outcomes. But it vindicates his insistence that interpretation matters, that we cannot simply use quantum mechanics without asking what it means. The Bohr model itself occupies a strange position in physics education and in the history of science. It is taught to beginning students because it provides an accessible introduction to quantum ideas, quantization, energy levels, quantum jumps. But students are quickly told that the model is wrong, that electrons don't actually orbit like planets, that real atoms are described by wave functions and probability distributions, not orbits. The Bohr model is pedagogical scaffolding, useful for climbing toward understanding, but not part of the final structure of quantum theory. This bothered some of Bohr's colleagues, who felt that his most famous contribution was being relegated to the status of a useful fiction, a step along the way rather than an enduring truth. But Bohr himself had always acknowledged that the model was transitional, a stepping stone toward a better theory. He had called it preliminary in his original 1913 papers. He would likely have been satisfied that it served this purpose, even if it meant his name became attached to something that was eventually superseded by more complete theories. What endures most powerfully from Bohr's work is not any specific model or equation, but an approach to physics and a set of questions about knowledge, the insistence that interpretation matters, that physics is not merely about mathematical formalism, but about understanding what nature is telling us about reality, and the recognition that this understanding might require abandoning intuitions built from everyday experience. The complementarity principle, whether accepted or rejected in its specific form, established that quantum mechanics forced physicists to think differently about what it means to know something about the physical world. It challenged the assumption that nature exists in a definite state, independent of observation, and suggested that the questions we ask and the way we observe fundamentally shape what we can know. These ideas influenced fields beyond physics, from biology to cognitive science to philosophy of mind, even if their application in those domains remains contested. They represent Bohr's attempt to understand not just atoms, but the human relationship to knowledge itself. Bohr's political legacy is more ambiguous but perhaps more important than is often acknowledged. His advocacy for international control of nuclear weapons failed in its immediate goals, but contributed to a broader movement of scientists engaging with policy questions, refusing to accept the separation of knowledge and responsibility. The tradition of scientists speaking out on issues where their expertise gives them moral authority, whether climate change, genetic engineering, artificial intelligence, or other potentially catastrophic technologies, owes something to Bohr's example of refusing to remain apolitical in the face of dangerous knowledge. That this engagement often proves ineffective does not diminish its importance. Bohr demonstrated that scientists cannot ethically claim neutrality about how their discoveries are used, that the pursuit of knowledge carries responsibility for its consequences, that expertise creates obligation. This lesson has not always been learned or applied, but it has been articulated with particular clarity through Bohr's example and advocacy, and it remains relevant as new technologies create new risks. Return now to October 1943 and the Bombay of a British mosquito climbing through cold autumn air above the North Sea. The physicist who lies there suffocating, consciousness fading, embodies a civilization's contradictions at their most acute. He has devoted his life to understanding nature, and that understanding has produced both enlightenment and horror. Both the foundation of modern technology and the means to destroy civilization, he has sought to transcend nationalism through science, creating an international community of scholars pursuing truth together, and now he is fleeing occupation while being smuggled to work on a weapon that will kill hundreds of thousands. He has championed openness and collaboration, and now he operates under a transparent alias, carrying secrets that cannot be shared with most of the world. He has argued that physics describes what we can say about reality based on measurements, not reality itself, and now he carries knowledge that will reshape political reality across the globe in ways he cannot fully foresee. The suffocation is almost metaphorical, a man being crushed by the weight of consequences he never intended but cannot escape, bearing knowledge that has become too heavy to carry. But he does escape, just barely. He survives the flight, works on the bomb, witnesses its use from a distance, returns home to a changed world, and spends his final 17 years trying to prevent the nuclear catastrophe he fears, knowing his efforts will likely fail but unable to accept failure as final. Whether this effort was futile or essential remains debatable. The world did not destroy itself in nuclear war during Bohr's lifetime or in the 60 years since his death, though it came close several times. Whether this restraint resulted from the efforts of scientists like Bohr advocating for arms control, from political calculation and deterrence theory, from simple luck, or from some combination cannot be determined with certainty. What is certain is that Bohr felt he had to try, that simply accepting the logic of nuclear arms racing as inevitable was for him an abdication of responsibility, a betrayal of everything he believed about knowledge and its proper use. The scientist who had revolutionized physics by recognizing that uncertainty was fundamental to nature at the quantum level could not accept uncertainty about humanity's future as inevitable or acceptable. He fought for a world where knowledge served human welfare, where understanding nature led to flourishing rather than destruction, where the international community of science could model cooperation for political leaders to follow. That he failed to achieve this world does not diminish the fight or the vision. His life traced an arc from the pursuit of pure knowledge in an optimistic era to confrontation with the catastrophic consequences of that knowledge in a tragic century. The Copenhagen of his youth, where science was discussed in his father's dining room with genteel enthusiasm, where the pursuit of knowledge seemed innocent and noble, gave way to the Copenhagen of his maturity, where physicists from across Europe gathered to revolutionize humanity's understanding of matter, where scientific internationalism seemed to transcend the petty divisions of nationalism. That scientific cosmopolitanism was shattered by war and occupation, and the weaponization of physics by the discovery that knowledge was power, and power could be used for destruction as easily as creation. The Copenhagen he returned to in 1945 was physically intact but spiritually altered, a city in a world where the innocent pursuit of knowledge had proven impossible, where every scientific advance carried potential for destruction, where the questions "can we" and "should we" could no longer be separated as they had been in the optimistic 19th century. Bohr never reconciled these contradictions because they cannot be reconciled through any simple resolution. The same quantum mechanics that explained the periodic table and chemical bonding, that enabled transistors and lasers and all of modern electronics, also enabled nuclear fission and fusion and weapons of mass destruction. The same scientific internationalism that made the Copenhagen Institute a model of collaboration also meant that nuclear knowledge would inevitably spread beyond any one nation's control. The same drive to understand nature at its most fundamental level that led to the Bohr model also led to the atomic bomb and the hydrogen bomb and all the weapons that followed. These are not separate phenomena that happen to be connected, but aspects of a single phenomenon, the power and danger of human knowledge. Bohr's life demonstrates that this power cannot be renounced without abandoning the quest for understanding entirely, and this danger cannot be eliminated without ending the pursuit of knowledge. Physics will continue revealing nature's secrets, and those secrets will continue being used for purposes both beneficial and destructive. Scientists will continue being both the generators of knowledge and the witnesses to its consequences. What Bohr's example offers is not a solution to this dilemma. No solution exists that would eliminate the contradiction, but a way of living within it with integrity and purpose. He refused the comfort of specialization, the retreat into narrow technical work that would have absolved him of responsibility for broader implications. He insisted that scientists must engage with the broader implications of their work, that understanding the atom was inseparable from understanding what that knowledge meant for human civilization. He rejected the separation of facts and values, the claim that science was neutral and that scientists bore no responsibility for how knowledge was used. He argued that understanding nature required philosophical reflection on what that understanding meant, that you couldn't separate the empirical question of how nature worked from the conceptual question of what it meant that nature worked that way. He resisted the temptation to claim that the uses of knowledge were someone else's responsibility, taking upon himself the burden of advocacy even when it proved ineffective, even when political leaders dismissed him as naive. And he maintained, despite everything, the conviction that understanding was worth pursuing, that knowledge was valuable even when dangerous, that the human project of comprehending reality remained meaningful even in the shadow of extinction. This was not blind optimism, but a deliberate choice to continue the work of understanding despite being fully aware of its dangers, to insist that the proper response to dangerous knowledge was not ignorance but wisdom, not retreat but responsibility. The atom that Bohr first explained in 1913 was a simple thing in his model, a nucleus with electrons in discrete orbits, absorbing and emitting light in quantum jumps, following rules that couldn't be justified from classical physics, but that matched experimental data perfectly. The actual atom proved far stranger than even this revolutionary model suggested, described by wave functions that exist in probabilistic superposition until observed, with properties that depend on the questions asked about them, behaving in ways that violate human intuition but match experimental reality with extraordinary precision that has never been contradicted. This journey from simple model to strange reality mirrors humanity's broader journey from the 19th century's mechanistic certainty to the 20th century's quantum ambiguity to the 21st century's technological power, coupled with existential vulnerability. Bohr was both the guide who initiated this journey and the traveler who experienced its costs most fully. His life was the quantum transition of physics itself, a leap from one state to another, releasing energy that illuminated and destroyed, leaving the world fundamentally and irreversibly transformed, unable to return to the innocence of the previous state. He saw further than most into the nature of reality, understanding atoms and nuclei with a depth that few achieved, and he saw more clearly than most the moral implications of that understanding, recognizing that knowledge created responsibility, that power demanded wisdom, that understanding nature meant understanding our relationship to it. The tragedy was not that he failed to prevent nuclear weapons. No individual could have done so once the basic physics was understood, but that civilization failed to develop the wisdom to match its power, that humanity learned to split atoms before learning to govern itself. That knowledge raced ahead of ethics. And yet he persisted in believing that understanding mattered, that truth was worth pursuing, that science remained humanity's best hope for comprehending reality and perhaps for surviving its own power. This persistence in the face of tragedy, this refusal to abandon understanding despite its dangers, this insistence that knowledge and responsibility were inseparable, these constitute Bohr's ultimate legacy, more important than any equation or model, more enduring than any scientific discovery. He showed what it meant to be a scientist in an age when science had become powerful enough to destroy the world. Not neutral, not withdrawn, but engaged, responsible, and relentlessly committed to understanding despite all its costs.